Welcome. We're getting closer. We can almost sense it. All right. You can stick with me. Come on. All right. This is section 5.4, Fundamental Theorem of Calculus. Fundamental Theorem of Calculus. Do you think it's important? It is fundamental. Okay. So I think it is, and there are two parts to this theorem. We're going to spend quite a bit of just today dealing with the first part. It says, if little f is continuous on a closed interval a to b, then there exists a function, a capital F, that is the antiderivative of f. In other words, if I have a continuous function that I can take the, if I have a continuous function, then I can, go backwards. Instead of taking the derivative, I can go backwards and come up with a brand new function. And we're going to call it capital F. Okay? Does it make sense? Okay. And then the second part says that if I have the function f, okay, which is my antiderivative, so the antiderivative of little f, okay, which is capital F, has a derivative at every point, okay. So again, here is this is capital F is this part right here. This piece, that's capital F, okay, that's what's up there. So if I take the derivative of capital F, hey, that's the same as saying f prime. And I said, well, f was the antiderivative. Okay, capital F was the antiderivative, big F. So if I take the derivative of big F, I'm going to get the function that I started with to begin with. And this is actually where we're going to spend our time dealing with today, but we're going to go through a little exploration with it. All right? Okay, here we go. So I'm going to first start off with the top part here. Okay, I'm starting here. That is, give a geometric area interpretation of capital F using the vertical line segment shading. Okay, so what that means is I'm going to take some vertical lines here, and I'm just going to shade in what it means to be the integral from a to x of my function f of t. So I'm just going to shade in some vertical lines here. Okay. Step 2. To see how the value of f changes at various points, mark another point, x plus delta x, on AB using diagonal stripes. Shade the region given by the definite integral a to x plus delta x. Okay. So, well, x plus delta x. So what I'm going to do is I'm going to have some delta x. Let's grab this here. Okay. And here's delta x. Okay. There's x plus delta x is right here. That little section there is delta x. I'm going to line this up. And then I'm going to do cross or diagonal from a to x plus delta x. Okay. And so what is that going to be? Well, if f of x is that, this is going to be f of x plus delta x. Does that make sense? Because f of x before was just f of x, it had the x up there. F of x plus delta x, because it's x plus delta x here. See? F of x here. Okay. So far, so good. All right. I move on. And I'm going to have my shading over here real quick. Okay. Here's my x plus delta x. And I'm going to shade in what it was here. There's that. And shade in the diagonal. It says here, show geometric interpretation of x plus delta x minus f of x by shading in a color. Okay, so if you have a color, great. Okay, if not, I'm going to shade that in. So f of x plus delta x was the whole red section here with the diagonals. The blue section was just capital F of x. I'm going to subtract the two, and what am I going to be left with? This section right here. So if you want to shade it in, shade it in. It says here, since the striped color region is roughly rectangular in shape, okay, its area can be approximated with a left rectangle. So here again, here's my colored area right here. I'm going to do its width. The width is x plus delta x minus x times my height, which is f of, again, left rectangle, so it's going to be f of x. So therefore, I can go ahead and write this, okay, this region as little f of x times delta x. Solve for f of x in this approximation. So I'm going to go ahead and do that. So when I approximate this, I can just say then that f of x is going to be equal to, well, big F of x plus delta x minus f of x all over delta x. Since this estimate more closely approximates the actual value of delta x gets smaller, take the limit as delta x goes to 0. Okay. Okay, so I want to take the limit as delta x goes to 0. So let's go ahead and write that. I'm going to take the limit of delta x goes to 0. Okay. I'm going to say that that's going to be equal to f of x of capital X, there we go, minus capital F of x all over delta x. Now, am I going to evaluate this limit? Okay. What you should be seeing here, guys, is this should look a little bit familiar. This should look like our limit definition of a derivative. Okay, where we had the x plus h minus f of x all over h. Okay, and so when I take my limits and I do this, what I'm able to see here is that f of x is really going to be equal to, well, that's just the limit definition of the derivative for my function capital F prime of x. Okay, so again, here's my f of x, and what I can do is substitute f prime of x with the integral expression, okay, in our fundamental theorem of calculus that we had before. If we talk about s, there it is. Okay. Ta-da. So when I take where a is any number, okay, so let's go over here and take a look at it. Next one. So substituting f prime of x with the integral expression gives us this here, which is what I showed you there. Okay. Gotta take this in for a moment. Okay. Let's read this together. In other words, the derivative with respect to x of the integral of f from any number a, to x is simply f in terms of x. This says that even continuous functions f is the derivative of some other function. Ooh. Likewise, the first portion of this tells us that the definite integral of a continuous function is a differentiable function, capital F, in terms of its upper limit of integration. In other words, when it says upper limit of integration, it means in terms of x. So let's see how we can use this in actual problems. Okay. Before we get there, we'll get that in a second. I want you to see what the effect of changing the lower limit of integration. Okay. What is this? What happens if I change a? Okay. So what I want you to do is I'm going to pause the video. I want you to graph both these things on the calculator, and I want you to sketch the graph over here. It will take some time for your calculator to graph these. Okay. You're going to make y1, put this into y1, graph it. Put this one into y1, graph it. Okay. Explain what has changed and maybe why it has changed. Okay. And we'll go through that when we get done. But I'm going to pause it. You guys do it and sketch the graph. And boom, there are your graphs. So I wanted to explain why this has changed. So here's my graph. It looks very much like a x cubed, and then there's this one that looks like kind of straight out of there, and it crossed here at 5, the x-axis at 5. So what you should explain why this has changed. Okay. Remember, when you put this into y1, you're creating a function, right? So f of x is equal to the integral from 0 to x of t squared dt. So when I put 0 in for x, okay, f of 0 is equal to the integral from 0 to 0 of t squared dt. And this is where you got to remember, well, what does it mean to take the integral from the one number to the exact same number? Oh, well, that's always 0. And that is why it goes, why it's 0, why it crosses here. So 0 to 0, that's why it's 0 there. Okay, so f of 0. However, when I do the second one, and I'm going to call it g of x, is equal to the integral from 5 to x of t squared dt. Okay, well, what is g of 0? Not g of 0, excuse me. G of 5. Well, that's going to be equal to the integral from 5 to 5 of t squared dt, which is equal to 0. Ta-da. Okay. All right, let's go next. Oop. Sorry about that. Gave you actually the same one over again. I didn't mean to do that. Here we go. Oh, whoops. Okay. Actually, it's not the same one. So now let's do this a little bit differently. Okay. Notice what's different. So in here, I want to graph this one into y1. Okay. And I'll graph the same one into y1. Now what's different? It's the derivative. Okay. So what I want you to do, so when you graph this on your calculator, you're going to go y1 is equal to d dx. And put that in there. Integral from 0 to x of x squared dx. And see what you get. Alright? And do it for the second one, and we'll find out what the surprise is. Surprise! It's the same graph. How is that possible? Well, again, remember, when I take the derivative, it doesn't matter what my number is here. Okay? That's what that theorem that we just went through, that we just proved, it just showed. Okay? It doesn't matter what our number here is. When I take the derivative of the integral, it's always going to be my function is always going to be, that my answer is always going to be the original function, which in this case was x squared. Kind of cool, huh? So how can this work in like real life problems? So if I'm being asked to do this here, this one here, what is the derivative of the integral of negative pi to x of cosine t? So the thing I check here, I see, well, is my bottom one a number? Yes. Is my top one an x? Yes. Oh, well, when I take the derivative of the antiderivative, it's like saying multiplying when you need to multiply and then divide. Okay, my answer for this first one is just going to be cosine of x. And I do the same thing for the second one. What is this going to be? The derivative of the integral. Again, I check, do I have a number on the bottom? Yes. Do I have an x on the top? Yes. Okay, so what's my derivative going to be? It's just going to be 1 over 1 plus x squared. It's that simple. It really is. Okay? Oh, but now I have another problem. Okay? I'm going to make this a little bit bigger so you can see it better on your computer screen. Okay? So this one here says, hey, I have the derivative. Okay? I want to find the derivative of this. Bottom one's a number. That's okay. The top one, though, is x squared. So I'm going to use the chain rule in this. And what do you mean by chain rule? Well, what I'm going to do is I'm going to set u be x squared. Okay? And so I want to go ahead and I'm going to say, well, let's go ahead and make y equal to the integral of 1 over u, or 1 to u of cosine t dt. Okay, and so now it's going to ask me, asking me to find dy dx, but what I'm really going to do now is I'm going to take the derivative of y, so I want to find dy du. Okay, well, dy du is the same thing as saying, well, take the derivative with respect to u of my integral from 1 to u of cosine t dt. Again, I check myself. I check, hey, is my bottom one, is my top just a single variable? Well, that's true. Okay, well, dy du is going to be equal to, by the fundamental theorem of calculus, just cosine of u. But I don't want dy du. I want dy dx. Well, what can I do? Well, if I take the derivative of u now with respect to x, I actually get du dx is equal to, take the derivative of that is 2x. Okay? And there's something else that I notice. Remember when I told you can't multiply these, right? Okay? So what I notice is that if I were to treat these like as multiples, if I take dy du and multiply it by du dx, what happens here? The du's cancel, and I end up with dy dx. So let's do that. Dy du is cosine of u times, okay, du dx, which is 2x, and that's going to equal dy dx, which is 2x cosine x, cosine of u. But again, I want everything in terms of x, so that's going to be equal to 2x cosine of x squared. I just replace it in there, and there's my answer. Okay. In general, the way that this is going to work out, it's always going to be cosine of u right down here. It's going to be whatever the function was originally with the upper limit there, times the derivative of the upper limit. Always. Okay? Let's see what we got next. Okay, so again, I want to do this one. Okay. Letter A is fairly straightforward. This one here, the x is not on top and the number is not on top. I can flip those, but what you have to remember is what? When I flip them, okay, I would now have to say, well, this is now going to be the negative integral from 5 to x of 3t sine t dt. And now I want to take the derivative of that. I want to take the derivative of this whole thing. Okay, the negative stays. I go from a number to a letter to x now, so I'm good. So now it's going to be negative 3x sine of x. And there's my answer. Okay. For part B, it's a little bit more complicated. Okay, so what you're going to have to notice here again, if I have a graph, here's my graph, and I'm representing the integral from 2x to x squared, and generally x squared is more than 2x. Again, I can represent the integral from 0 to 2x from here, and I could represent the integral from 0 to x squared as this whole part here. So if I take the integral from 0 to x squared of my function and subtract the integral from 0 to 2x of my function, I will get my answer. Okay? So that's what I'm going to do. But what's my function? My function is, oh, this should be t, my bad. My function is something super crazy. Okay, and again, I'm going to follow the flow. If I'm going to take the derivative of this whole business here, okay, if I'm going to take the derivative, I can do it one step at a time. Okay, I'm going from a number to a x squared. So what was my pattern? My pattern was put in the x squared wherever the t is. So my pattern says it's going to be 1 over 2 plus e to the x squared. times the derivative of x squared, 2x, minus the same equation with the u put in, or the 2x put in there, 2 plus e to the 2x times the derivative of 2x, 2. And you can leave it like that. And there's my derivative. Pretty intense, huh? But not too complicated, I don't think. With that being said, I know it's been long, but here is your first part of your homework. Take your time with it. Ask me questions when you get a chance to. All right? Bye.